I'm an assistant professor from Virginia Tech. Welcome to this ICSI technical paper session about testing and debugging. I'm the session chair, and Dr. Marcelo de Morin is the co-chair. Sorry for my pronunciation. And the first presentation is studying the use of Java logging utilities in the wild. The presenter is Goguryeo Chen from York University. Goguryeo, please.
Can you see my screen? Okay. Hello, everyone. My name is Goguryeo Chen. I'm currently a PhD student from York University, Canada. Today, I'm going to present our paper studying the use of Java logging utilities in the wild. This paper is co-authored with my supervisor, Professor Jianmin Jiang. Let's get started. First of all, what is software logging? Software logging is the practice that developers instrument logging code into the source code to record runtime behavior. This code snippet shows such an example. Depends on whether the logging authentication is successful or not. Two logging code will be executed in the runtime to generate log messages. Compared to the default way to use console printing to print log messages, such as system.out, here we use the logging utility to provide support such as multi-thread support, timestamp, and filtering mechanism such as verbosity level. Here we use log4j, which is a popular logging utility for Java. So during runtime, it will generate log messages like the following. Other than log4j, there are many logging utilities in the wild exist, such as SL4j, Android logging, Java logging, and the new logging utilities has been constantly introduced, such as Google's Flogger. We have examined existing studies on logging code, and we find out they are mainly divided into three categories: where to log, what to log, and how to log. Where to log is about deciding the appropriate logging points. What to log is about providing sufficient information in log messages. And how to log is about developing and maintaining high-quality logging code. And we have found out that although all those papers are published in top venues like computer systems and software engineering, like OSD and ICSI, but we have found out that only two papers have discussed a bit on logging utilities. One is about logging library migration. The other one is on log configuration. Hence, we feel it's very needed to study the use of Java logging utilities in the wild. We first conduct a quantitative study starting from GHTorrent, which is a very popular code repository database. We set a few filtering mechanisms, such as the number of stars and the programming language, and whether the project is a fork project or not. To this end, we have extracted 25,611 projects. Then, we further filter to see whether this project uses any logging utilities, and whether this project is a tutorial project or its size is very trivial. Then we conduct static analysis to check the import statements in the source code to check whether the project actually used RUs, like what kind of RUs they are used. And we extract a number of RUs. In total, we have 3,856 RUs extracted. We further divided these RUs into two parts: the external LUs and the internal LUs. For external LUs, the LUs are directly imported from the third-party library, such as log4j, as you see before. And the internal LUs are implemented inside the source code, directly by the project. This figure shows a brief summary of our results. We first categorize the size of the projects into four parts: small, medium, large, and very large projects. The y-axis here shows the number of RUs used in each project. And as you see, for small projects, most of the projects only use one RU, which is normal. But as the project size increases, such as medium-sized projects use at least 2 LUs for 50% of the project, and large LUs and very large LUs use more than that. So it's clearly that the use of LUs is more complex as the size of the projects increases. Motivated by this quantitative study, we want to further conduct a qualitative study to study the behind rationale. We have conducted this study on two kinds of projects, which is open source projects and industry projects. For open source projects, we study the external LUs, internal LUs, and the rationale behind multiple LUs. For the industrial projects, we basically conduct interviews on 13 developers from multiple famous large-scale companies such as Facebook and Alibaba. Due to time constraint, I will only go into details about the external LUs usage. Here, the table shows a brief summary of the use of top 100 external LUs used in the projects. We have seen that on the first column of the table, there are 4 rationale, which is general purpose, LU interaction, internationalization, and modularization. In the second column, it shows the percentage of the external LUs being used for each of the rationale. In the third column, it shows the number of projects the percentage of projects use such LUs with the rationale. And the last column, which shows the example of this for each of the rationale. Due to time constraint, I will only go into details about LU interaction and internationalization. As general purpose, you guys have already seen an example before for the log4j. And for modularization, people mainly implement this mechanism using aspect-oriented programming. Let's first take a look at LU interaction. This code snippet is from a project called Bitcoin Wallet. It uses OKHTTP3 to build HTTP connections. So in order to know better, to know what's going on inside the OKHTTP3 and to improve the visibility, we need to use the logging utility provided by OKHTTP3. So here we use the logging interceptor. In this way, we have a full observability of either this particular project, Bitcoin, and also the third-party library, OKHTTP3. Next example is for internationalization. This code snippet uses JBoss logging, and this code snippet is from Hibernate, which is a popular ORM framework used around the world in many countries by many people. So these log messages use the annotation, such as here, the log message and message to define the verbosity level and the static text. Then in practice, if you want to use such a logging facility, you need to directly invoke the API. In here is a cache file not found. And what's more interesting is, if you want to provide the log messages to people who use multiple human languages, you just need to write separate property files to define the translation. So in here, the English log messages was translated into Chinese. So in summary, you could see that LU interaction accounts for 83% of the external LUs, and which is the most majority ones. So tools for better management and configurations for LUs are definitely needed. For third-party libraries are definitely needed. In summary, we first talk about software logging, and we show an example how this logging utility was used. And then we have illustrated that existing studies have touched very little on logging utility. There are only 2 papers that discuss the logging utility. So we conducted a quantitative study, and we find out that the use of LUs is more complex as the size of the projects increases. Last but not least, we conducted a qualitative study on open source and industry projects to study the rationale behind the usage. So in the end, we have provided the replication package here. And if you're interested, feel free to check out our paper and play around with the dataset. And that's all. Thank you.
Thank you for the presentation. And I have a question from the Slido.
example, we see that when you use an external library such as OKHTTP3 or Netty, this kind of library, you want to know what's going on inside the library. So you interact with the area provided by them. But modularization is more like the way of conducting logging code. For example, in aspect-oriented programming, you set up a central aspect file where you put all the logging code there, and also define the rules, like whenever I occur, like for example, a method full or method bar, I will invoke the log messages like that. So these two are a different concept.
Okay, thank you for the answer. And I think we have probably some seconds.
I have a question. I'm not sure if I go ahead. I mean,
and what it took to understand and resolve the problem. Many of us, including myself, just had a nightmarish flashback, thinking about the time and effort that went into eventually fixing that bug, despite having a tool that was supposed to make it easier. We believe that one reason debugging is so challenging is because existing debugging tools, such as Tarantula, typically answer questions like what lines of code are correlated with the failing test that exposes the defect. However, recent work has shown that this information alone is not helpful to developers when debugging. What developers really want to know is what's causing the software defect. So we wanted to know, how can we help developers understand defect cause? To this, we began by exploring existing work on causality and landed on this notion of causal experimentation. Causal experimentation is the process of modifying and executing tests to observe causal relationships and derive causal claims about defect root cause. For example, let's say you're a developer working on some mapping software and you get a bug. From this bug, you'll try and reason about what might be going wrong, starting with maybe the addresses and noticing differences there, or thinking about the path and anything along that path that could be causing problems. Now, as implied, this process, if done, is manual and of course time-consuming. Now, imagine a tool told you that certain inputs failed, but these other very similar inputs pass. Upon comparison, it quickly becomes clear that failing executions start and end in different countries, but passing ones start and end in the same. Therefore, we propose a way of automating causal experimentation, which we call causal testing. Causal testing uses existing debugging techniques, like testing and fuzzing, with the goal of providing minimally different executions that expose defect cause. So, how does causal testing work exactly? Well, let's take a look back at the maps example. Here's our bug, which was found by this failing test. This test has an assertion with a method call and inputs to that method call. The first thing causal testing does is perturb the inputs to the method call and execute these new tests while keeping track of which pass and which fail. Lastly, and most importantly, causal testing determines which of these executions are most similar to the original failing test based on both the input and the execution path. While causal testing is novel, it is inspired by previous work in debugging. This includes work on input minimization with delta debugging, directed test generation, fault localization using observational data, and associating input features with program behavior. In contrast to existing work, causal testing generates new inputs and tests using a manipulationist approach to find executions similar to the original failing. Causal testing can also be used to test software for bias by seeing if, for example, changing gender or race changes outcomes. To evaluate our technique, we developed a proof of concept implementation called Holmes. I will now switch to Eclipse to show how Holmes works. Here, we have a failing test, as indicated by JUnit's output. This test takes a hex number as input, but something is wrong. Maybe Holmes can help. We can access Holmes through the pop-up menu here. When I click Run Holmes, Holmes produces the following output. We can see from the passing execution here that the problem lies in the use of an uppercase X in the original input here. Using our prototype, we conducted a user study to determine whether causal testing can help with identifying defect cause and fixing the defect. We also want to know how useful causal testing is. For this evaluation, we compared debugging with Holmes to using JUnit, the gold standard for testing and debugging Java programs. We found that, when using JUnit, participants could correctly identify defect cause 80% of the time, compared to an improved 86% of the time with Holmes. When it came to repairing defects, we found that participants were able to correctly repair defects most of the time with JUnit, with a slight increase when using Holmes. Now, being most Java programmers use JUnit, our goal with causal testing is not to make JUnit obsolete, but to complement JUnit and provide different useful information. And we do, which is fantastic. This is further supported by our usefulness findings, which show that majority of participants either found Holmes more useful than JUnit, citing the similar passing test as the most helpful, or equally as useful as JUnit. A small percentage of participants felt that JUnit was more useful, often citing higher familiarity with JUnit and its interface. But, as we intended, the majority of participants felt that Holmes and JUnit complement each other and both provide useful information for debugging. In addition to whether causal testing can help, we wanted to get a sense for how often causal testing can help. So we manually went through the defects in the defects per day benchmark to see when causal testing would work and when it would be useful. Of the 330 defects we manually evaluated, we were able to categorize with confidence 42%. Of that 42%, we found that for 71% of those defects, causal testing would work. This means that a causal testing tool, like Holmes, could find at least one minimally different passing test for the defect. Of the 71% where causal testing would work, we found that for 77% of those defects, causal testing would be useful. This means that the similar tests found by causal testing capture the defect's root cause. In conclusion, causal testing can help developers understand defect cause, plays well with others, and generalizes beyond our user study, as indicated by our analysis of real-world defects in the Defects for J benchmark. You can check out our full paper for all the juicy details. Thanks for your time.
All right. Thank you.
I have questions. I mean, if I have time.
I hope so.
Yeah, I think we have time for questions.
Okay, Brittany, right? Well, I have two questions. I mean, first is the number about the number of alternative tools that you generate. I mean, to provide these rationale of why and why not. I mean, that test works. And this is one question. And also, if you consider the handling like heap, no, I know structure inputs, right? I mean, like heap objects, I mean, this kind of stuff, in addition to strings, right? At least, I mean, and in examples that I saw, I've seen you giving examples on strings, but I'm not sure if this works. I mean, for different kinds, different types.
Great questions. So I'll start with the first about how many tests. And we found that in our study, as well as the manual evaluation of additional defects, that this would vary depending on the type of input and the amount of time that we're willing to take to find these additional tests. Sometimes causal testing or Holmes is able to come back very quickly with some additional tests. We have a cap that we set to minimize the time that it would take sometimes. So we would cap it at 3 additional tests per category, so that's passing and failing. But that cap can be changed, just it may take more time or more resources to get those additional tests. Now, in terms of the types of input, as you mentioned, in our study that we did so far, we used strings and primitive types as our proof of concept, but we did put some thought into what it might look like for more complex inputs, such as objects. And I think that becomes an issue of breaking the inputs down to these lower level types, strings, numbers, things of that nature, and then being able to make perturbations at that level, and then building back up these objects. Of course, probably taking, again, more time and resources to find these valid objects in that process. But that is one way that you could work causal testing into more complex multi-part objects.
Yeah, just I mean a quick feedback. I mean that there is a similar work. I mean upcoming on this ICSI or ASE. I'm not sure, or FSE, about Andre Zeller, which is kind of similar, right? I mean they generate like a decision tree based on these inputs, right? That explain when the test fails and when they do not fail. I mean so please take a look at it, and I really don't remember the name.
Absolutely, I'll definitely have to look for that, and I'm sure there'll be some interesting intersection there as well. Thank you.
All right, let's thank our speaker, Brittany, and I think we can move on to the next presentation. The next one is studying the characteristics of logging practices in mobile apps, a case study on F-Droid. The presenter is Jinfu Chen from Concordia University. Jinfu, please. Jinfu, I cannot hear you. I think you can start whenever you're ready.
It's okay now?
Good.
And the screen is okay?
Yes.
Okay, thank you. Yeah, sorry about it. So hello everyone, my name is Jinfu Chen. I'm a PhD student from Concordia University. Oh, sorry. Thanks for attending my presentation today. Today I will present our research paper about logging characteristics in mobile apps. Logging is very important in software system. Extensive prior study were conducted in characteristics of logging practices in servers and desktop applications. However, there exist few studies on logging practices of mobile apps. So in our research, we want to study the logging practices in mobile apps. We conduct our study on around 1,400 Android apps from F-Droid. F-Droid is a software repository for free and open source Android apps. Many apps in F-Droid are actively maintained and also published to the Google Play Store. Because none of the prior studies on logging characteristics are conducted on mobile apps. So first, we want to examine what are the characteristics in mobile apps. We measure different kinds of metrics to understand the logging characteristics in mobile apps, including line of source code, log changes, and the code churn rate, and the log churn rate. We studied these metrics because prior research also measures these metrics to understand the logging characteristics in servers and desktop applications. And finally, we found that the logging practices are different in mobile apps than server and desktop applications. we found that the mobile login statements are less pervasive and also less midterm compared to the server and desktop application. In particular, we also found that the mobile login statements are more often to be deleted. So why there exists such large difference in login characteristics between mobile apps and server applications? So we would like to study the rationales of mobile login to understand such difference. We conduct a firehouse email interview with the developers who recently added login statements into the source code. We first weekly monitor the FJoy apps to identify whether there exists the newly added login statements. If we observe a newly added login statements, then an email will be sent out to the developer. We will ask the developer in each email, why did you add the login statements in this situation? And finally, we send out in total of 189 emails and receive 63 emails during our study period. And then we follow an iterative approach to put all the responses into different categories. And finally, we identify 6 different rationales based on all the responses. And we found that the majority of the mobile login are for debug purpose. Such may explain that why most of the login statements are more often to be deleted. Another interesting finding is that developers often choose inconsistent log levels to the rationals. So for example, we found that around 23% of the login statements, they want to debug the system. However, they use the info, warning, error levels. So such may produce unnecessary log informations and also cause performance overhead. Therefore, we want to understand how large can the performance impact. We select 8 apps to conduct our studies based on the app's development history and also the number of the login statements. We apply 3 types of tests to measure performance, including the local unit test, instrumented test, and also the spectral test. For each test, we measure performance first, enabling all the login statements. Second, we measure performance disabling all the login statements. And finally, we measure performance only enabling the necessary statements. We measure performance metrics in terms of response time, CPU usage, and the battery consumption. To get more reliable performance data, each test will be executed 30 times independently. Finally, we found that there can be a statistical significant performance overhead when generated log in mobile apps. The maximum performance overhead is observed in our instrumented test in the K9mail application. The response time and the battery consumption with logging enabled is around 3 times of that without login statements. Our results call the need for automated approaches and also Turing support for login decisions of mobile app development. So that's all my presentation. So thank you for listening. I'm happy to take your question for now.
I have a question.
Yeah.
Go ahead.
So it's much more difficult to actually fetch logs from a mobile app than it is from a server that you control. Has that affected what kind of logging people do?
So does your questions mean how to extract the login statements from the mobile apps?
Right. Given that it's more difficult to extract a log from a mobile app than it is to extract a log from a server, does that change people's logging practices?
Yeah. Actually, in our RQ1, we show that there exists large difference between the login characteristics in mobile apps and server desktop application. And the biggest difference is that we can go back to this slide. And the biggest difference is that the mobile logging is more often to be deleted compared to the server and desktop application. And we've seen that the different characteristics of the logging practice in the mobile apps can introduce new challenges and also the opportunities for the mobile apps researchers and the practitioners to make the optimal decision for their logging in mobile apps.
If I understood correctly, I mean, the question was about how to measure, I mean, these timings, the cost of logging during the execution of mobile apps, because the measurement itself could introduce some noise, right? I mean, that's what I understood.
Okay, I think it's.
I didn't get it.
So I think maybe the presenters and askers can take the discussion offline. We need to move on.
Yeah, I think we can discuss maybe later.
Yeah, thank you, Jin.
Thank
so
you.
The next presentation is automatically predicting bug severity early in the development process. The presenter is Jeremy Bradbury from Ontario Tech University. Jeremy, please. For some reason, I cannot see Jeremy. So I'm curious, Martin, can we play the video? For Jeremy's talk.
Can someone call him on the green room?
Okay, let me try to.
Welcome to our presentation titled Automatically Predicting Bug Severity Early in the Development Process. I'm Jeremy Bradbury, and this work was co-authored by Jude Arokium. Bug severity is defined as the impact a bug has on the successful execution of the software system. Bug severity ratings are a common attribute of most bug reports, including the example of a trivial bug on the right side of this slide. Automatically triaging bug reports by severity has been previously addressed in the literature. For example, Severus is an approach that trains a keyword-based classifier using bug reports from the current project. The main challenge of this method, and others like it, is that it can actually take 70 to 90% of a project's bug reports to properly train the classifier, thus delaying when the triaging can be used in practice. The main motivator for this research, as we believe that in order for automatic bug report triaging to be effective in practice, it must be useful early in the development process, ideally from the first occurrence of a bug. Building on our motivation, we hypothesized that bug reports from an organization's past projects could be the key. More specifically, the way past project bug reports are written could be leveraged to accurately predict bug severity in a new project. We have developed a supervised learning approach that differs from previous work by using features of past projects instead of building a classifier by relying on the presence or absence of keywords in the current project's bug reports. In our approach, when a new project is initiated, the classifier is already trained and can predict bug severities immediately. We have evaluated our approach by comparing it with the Severus tool using the NASA PITS dataset. This is a data set of bug reports from 5 actual NASA robotics missions that are labeled with severities from 2 to 5, with 2 being the most severe and 5 being the least. In the interest of time, we'll only discuss our results with respect to F measure. From this first bar graph, you can see that our approach outperformed Severus in 3 of the 5 PITS projects, despite Severus being trained on data from those same projects. Furthermore, our method is effective at predicting bugs from the beginning of the project's history as opposed to from after the training has been completed. We ran separate experiments to assess what the best historical training data was for a given NASA PITS project. For example, should it be trained individually on one other project, pairs of projects, etc. The variations in the F measures for PITS C and D in particular show that not all historic data is effective. Thus, our method is only viable when the training data is representative of the test data. In conclusion, we have presented our new idea of using the past project bug reports to predict the bug severity from the start of a new project, and this work does not require any project or domain-specific classifier features. Our emerging results from the NASA PITS dataset show our approach does require semantic similarity between the bug reports in the historic and new projects to be successful. If you're interested, please look at our paper as well as all of our source code and data, which is available on GitHub. Thank you very much.
Hello, and thank you for coming to my talk on
So I have a quick question. What is your future work?
Sorry?
What is the future work?
That's a very good question. So actually right now, one of the things that we're doing is we're actually focused on evaluating technique on different organizations' projects. So we've been analyzing it on the Eclipse data set, on Bugzilla bug reports from Mozilla as well. So that's one direction. Another direction that we're also interested in looking at is how can we automatically identify what historical data is actually the most appropriate. As you saw from the box plot, there was some variation in some of the projects. And if the goal is to actually make this feasible and useful early in the development process from day one, you need to have some way of actually being able to quickly analyze or understand what historical data in your organization is going to be the most appropriate to use in a new project. I also just wanted to apologize. Zoom crashed right when I shared my screen, so that's for the delay. So.
Okay, that's totally understandable. All right, thank you, Jeremy. Let's move on to the next presentation. It's a survey on adaptive random testing. The presenter is Weifeng Sun from Jiangsu University. Weifeng, please.
Hello everyone, my name is Sun Feng. I'm from the Jiangsu University. Today, my focus of presentation is adaptive random testing, ART for short. My presentation is mainly divided into 4 parts: background, methodology, question answers, and conclusion. Let's start with the background part. Random testing is a basic black box testing method that can easily be implemented in practice and has a wide variety of applications. The figure shows the main idea of ART. Adaptive random testing makes use of information about field regions to improve the random testing's effectiveness. Its motivation is simple. A program input that is far away from non-failing causing inputs may have a higher probability of causing failure than the neighboring testing inputs. Since its introduction, research about development and analysis of ART has grown steadily. However, until recently, no up-to-date, comprehensive survey has been available. Our paper aims to address this. In our paper, we put forward 6 research questions to structure and categorize the available ART details and evidence. On the left side of this slide are 5 online literature repositories we stacked. In total, we read and inspected 140 primary studies. Now, let's move on to the most important part, the research question and answers. In this part, I will point out the general contents of our research. If you want more information, please read our paper. The first question is what has been the evolution and distribution of ART topics in the published studies. This slide shows the researchers and organizations based on the 140 primary studies, 167 ART authors, and about 41% of ART papers came from Asia. Now we can see that most papers have been published in conferences or symposia proceedings, followed by journals and then workshops. This slide shows the primary studies according to the main contribution and the research topic. Let's shift over to the second research question. What different ART strategies and approaches exist? First of all, the strategies and approaches we selected mainly satisfy the two basic rationales. Rationale 1. New test cases should be far away from previously executed non-failing causing test case. Rationale 2. New test cases should contribute to a good distribution of all test cases over the entire input domain. And then, we turn the existing ART algorithms into 6 different strategies, and shown on the right bottom side of this slide. For each strategy, in addition to providing its corresponding framework, we point out the key components and list all their implementations. This slide points out the main threats and the weaknesses of ART strategies. Question 3. In what domains and applications has ART been applied? Over 140 papers in our survey. The numerical programs have been the most popular domains for ART application, followed by object-oriented programs, embedded systems, and others. As for the fourth question, how have empirical evaluations in ART studies been performed? This, which involves two parts, simulations and empirical analysis. Simulations is to construct filters in the numerical input domain to resemble real testing. As we can see from this slide, most simulations have been conducted in low-dimensional input domain with lower filter rates, and the real program types mainly including C++, Java, and C#. And there are a total of 7 different metrics to evaluate effectiveness. The main 131 primary studies point out that F-measure is quite suitable for assessing effectiveness, and 8% of the studies adopted the F-time as the cost-effectiveness metric. The fifth question focuses on the misconception surrounding ART. Number 1, ART is equivalent to FS. Number 2, ART should always replace RT. In our paper, we provided explanations for them. ART still has several challenges and not resolved. In the last research question, we presented 6 main current challenges and possible solutions for them. As we saw and analyzed in previous parts, we classified the various ART approaches in different categories, investigated the ART application domains, identified that different types of filter patterns have been used in the variously reported simulations, and discussed some misconceptions about ART. Last but not least, we believe that this article represents a comprehensive reference for ART and may also guide its future development. Finally, thank you very much for your attention, and if there are any suggestions and comments, we can communicate later.
Good talk. So actually, I do not see waveform here, probably because of this network issue. In that case, I think we can move on, and we have the last but not least presentation, which is code level model checking in the software development workflow. The presenter is Daniel Norborn. So Daniel, please.
Can you hear me?
Yes.
Great. Thanks. So yeah, thanks everyone for coming to this talk on code level model checking in the software development workflow. I'm Daniel Schwartz-Narbonne. I'm a senior applied scientist at Amazon Web Services. And this is joint work with my team, including a number of interns. And the work I'm going to be talking about today in detail is a formal verification of memory safety, undefined behavior safety, and some functional correctness properties of C code. And if you want all the details, it's in the paper. But what I'm going to talk about today is more sort of the experience that we had while doing this work. because our team has literally decades of formal verification experience across multiple companies. And this engagement was different in some ways from ones that we've done before. And I want to talk about how and why. Like I said, the details are all in the paper. And the key takeaway is that we started seeing developers writing specifications in a way that we hadn't before. So I don't think I need to convince an ICSI audience that specifications are a good thing. And I don't think I need to convince an ICSI audience that developers are the best people to write these specifications. And sadly, I also don't think I need to convince an ICSI audience that developers don't write as many specifications as perhaps ideally we might wish for our purposes that they did. And yet, look at this. During the engagement to verify this C library that we talk about in the paper, developers started adding code contracts themselves to the code. And this is something in a scale that we had not really seen before. And so the question is, what happened? Why are developers adding these contracts themselves? And I think it's because our formal verification engagement really focused on turning proof into a social process and getting inside the developer workflow and providing direct value to them in terms of the formal verification. So one of our key insights is that you have to use artifacts that fit within the developer's workflow. And so we actually wrote our specs and our verification proofs in C. So if you see here, this is a proof harness for one of the data structures, for one of the functions in the AWS C Common Library. It looks like a unit test. In fact, if you're a developer and you see this, you know how to read a unit test. You know how to read this. You know how to comment and how to review a unit test. You know how to comment and review this. And it's a very small delta for them to be able to enable formal verification since they already know how to do testing. We embed the specs in the code. So you see here, there are these pre and post conditions. These are runtime assertions in their code that are checked when their tests run. And I'll talk about the value that this provided. But this is, again, putting it in C, in their code, in their workflow. We embed it in their workflow also by providing continuous value. Formal verification provides a snapshot that said, at this second, this code was probably correct. But what we do is we actually embed all of our formal proofs into the CI system. So if you've ever used GitHub, you know you do a PR, you get a whole bunch of check marks and X's from all your tests that run. We run our formal verification proofs like they were tests and give them check marks and X's. That means the developer who's developing and sees check marks can actually increase their velocity because they know that the code that was verified correct is still correct. And a developer who's developing and sees X's immediately gets a preemptive notification before it hits customers, before it affects our end users. They know that there's a potential issue and they can fix it right away. And this is another key thing. When we started working, you find a lot of bugs. It's the same problem you have with, for example, fuzzing tools. You find lots of bugs, but what you're doing is you're creating work for developers, right? You go to a developer and you're like, we found a whole bunch of bugs in your code. And they're like, thanks. You go to a developer and you say, we found a bunch of bugs in your code. Here are a bunch of patches that will fix, we believe will fix all the issues that we detected in your code. And now instead of creating work for them, you're actually creating a benefit for them. Now the developer says, oh, my pager's not going to go off. I can sleep better at night. Thank you very much. And so sending patches is orders of magnitude better than sending bug reports. So what happened? So let's look at this very simple data structure from the library that we were verifying, right? It's basically getting around the fact that C doesn't have arrays that are tagged with their length, so we build one. So they build one of them. So there's a pretty obvious specification here, right? The length should be less than or equal to the capacity. The buffer should be a non-null pointer into valid memory of at least size capacity. Tell it to developers. They're like, yep, sounds good. And remember I said we assert our properties in the code? So we actually added these as assertions and the unit test started failing. And turns out that some code will only assign buffer if capacity is non-zero. And the first developer says, yeah, that's what we intended. We have a shortcut. If you assign a zero capacity, we don't bother assigning the rest of the fields because they're meaningless. And the other developer is like, I really want those fields to be meaningful because I want to be able to do null checks on capacity, on buffer. And we actually triggered a real discussion between the developers that led to consistency and better documentation in their code. Another example, catching bugs downstream. So again, we verified the AWS Common library, and we inserted these runtime assertions. And guess what? The AWS CIO library had a unit test failure. Turns out that they were using one of the modules from AWS Common in a way that was outside the expectation of the AWS Common developers. So you provide value through formal verification, again, by getting within their workflow, by saying, we're going to help protect you against upstream failures by ensuring that your specifications become the contract that upstream users have to follow. So now specifications are a direct value to the user, direct value to the developer, because the upstream has to follow them. And finally, it simply is value because verification got better, and that provided value to the developers. So an example, the developer team was writing a ring buffer module. And they sent a request to our team. They said, you guys are really good at finding bugs. Would you mind taking a look at the PR before we ship it, make sure that we got this right? And because we had this strong relationship with the team, because we had a defined way of writing specifications, and we really understood the code very well, we were able to turn around and write a proof of their new module within a day of the request. And they merged that into master with the same commit as the code. In fact, we got verbal feedback from the engineers that this provided them with more confidence than the unit tests they had written for the same code. So shipping code with proof provided them with confidence and actually expedited their development process. So what's the result? We've seen rapid and predictable proof development of a kind that we had not really seen before in some of our previous engagements. So in this case, we verified 9 modules from this open source library. You can see everything on GitHub, and we describe it all in the paper. And this work was done in 24 weeks by 1 full-time engineer and 2 interns. And we've seen similar progress as we continued working on other engagements. We found a whole bunch of issues, and I talked about that. That's great. It's great to find issues. It's great to protect our customers because the issues don't, we find the issues early. And they were a range of severities. In fact, they were confirmed. These are confirmed from the development team, the severity and the type of issues that we found. But here's the thing I'm proud of. 100% of the issues we found were fixed. And if you look at the paper, a median time to fix was less than a week. And that's because I believe we provided not just bug reports, but patches. And they didn't always accept the patches we sent them. Sometimes they would push back and they would say, no, this isn't the fix we want to see. But starting with a patch leads to such a different interaction. It leads to the bug fixes, and that's what provides the actual value to our actual customers. So the takeaway is developers are writing specifications, and your verification engagement may be very different. You may be using different tools. You may be talking with different developers, but this, to my mind, is what you should focus on. How to get inside the social process of the developer so they want to write the specification. And if this work seemed exciting to you, we're hiring interns. If you're a grad student who's doing great work, email me. If you're a professor whose grad students are doing great work, email me. We'd love to talk to you. We're hiring interns. And as you can see, sometimes we even publish. Thank you very much. Any questions?
Hey, Daniel, I have a question for you, a quick question. I saw CNBC a few times over there, and you mentioned proof one way, and then I mean you also mentioned like run checks. So I got a bit confused. I mean exactly what you're using, what kind of properties you're using, and what kind of tools. From what I understand, CBMC is bound model check, right? So
right. So CBMC is a bounded. CBMC is a bounded model checker. We run it in the mode where you can actually turn on an assertion that requires all loops to have been fully unwound. So we run it in a mode where we don't count something as a proof unless we're able to get it through with unwinding all loops. Sometimes this does require us to do essentially a small model theorem where we say that we're verifying data structures up to a particular size of the structure. There's normally then sort of a pencil and paper side proof that says, there's nothing in the structure that would matter if you get to a larger size. We also confirm that with the developers. And we have ongoing work to try to remove some of the bounded model checking and go directly to specifications. But the other thing that we're doing, so if you look at what the proofs look like, and you can see this actually in the GitHub repo if you want to take a look at it, and I'm happy to chat about this more afterwards. We make a minimal set of assumptions about each data structure. We call the function, and then we assert a bunch of properties afterwards. And what we said is that the minimal set of assumptions that we make about the data structures that are inputs to functions should also be runtime checked when unit and integration tests run. And so that gives very high confidence that the assumptions, the environment assumptions that you have to make in order to set up data structures in order to be able to call a function to do a verification are in fact valid because they are checked against the unit and the integration tests. And it also, I found, really focuses the mind of the developers. It's one thing to say, here's a verification harness, does it look good? It's another to say, here's a verification harness, and all of the environment conditions in this verification harness, I'm going to put as runtime assertions in your code. Are you still okay with that? And if they say okay to that, that's a very strong signal. Now, it's true, there could be, this is not like 100% guarantee with proof. All formal verification, all verification sits upon some basis of you have to model something. What we're trying to do is we're trying to sort of, again, by getting inside the developer workflow, to drive assurance as high as we can.
Sure.
We have to talk more after.
I mean, just a quick question is about the cost. The cost of writing these patches, right? I mean, are they typically trivial? I mean, once you find bugs. I mean, because if they are, this is like a strong message for these people that work on automated repair, right?
Most of the patches were fairly trivial. They were things like adding null checks, or they were things like, in some cases, like with the initializer function, instead of having the shortcut behavior saying, in the case where the capacity is 0, we're actually going to want to zero out the other fields rather than just having capacity 0 and the other fields arbitrary values. There were a few cases where there were sort of interesting functional things that we had to thread through, but most of them were fairly, once you saw what the bug was, it was fairly obvious what the patch was. Yeah, so this could actually be a good test case. And since it's all on GitHub, you can just go and pull up all the PRs that added patches to this code and see if your tool would work well reproducing that.
All right, good. Thank you, Daniel. I think we ran out of time. And this is the end of this session. Thank all the audience for your attendance and patience. And so we will attend another session in 5 minutes. Thank you.
Everybody went well.
5, Testing and Debugging 2. My name is Marcelo Damorim. I'm from Federal University of Pernambuco. It's a great pleasure to be here and to host this session. The first talk in this session is going to be efficient generation of error-inducing floating point inputs via symbolic execution by the presenter is going to be Goguryeo. So it's all yours, Goguryeo.
Thank you. My name is Goguryeo. I'm a PhD candidate at UC Davis. Today, I'm going to present a joint work with Professor Cindy Rubio on error-inducing floating point input generation. We know that floating point arithmetic generates and propagates rounding errors, and the rounding errors will be accumulated into the program result. That is to say, the output of a floating point program is associated with an error. In most cases, the error is small, but there's some cases that the error can be very large. So knowing what input will trigger large error in your program is important. This is the problem we try to solve in this work to generate floating point inputs to trigger large numerical error. The state-of-the-art error-inducing input generators falls into two categories. In the first category, the techniques are based on randomness. They treat the program as a black box, and they use a set of heuristics to generate error-inducing inputs. So this category of techniques are inefficient, especially when the input space is large. The second category of techniques are using condition number. They treat the program as a function on an input variable x. So they compute the condition number of the function with regard to x to generate error-inducing inputs. This category of techniques can only handle one input variable. So in this work, our task is to generate error-inducing inputs for programs with multi-dimensional inputs, which indicates that the input space is very large. First, we observe how inputs can trigger high error. We use a program that implements recursive summation as an example. In this program, it takes an array as input and computes the sum of the array elements. We manually crafted an input array A. This input array A will trigger a high error in this program. Specifically, there's 3 additions. In the first addition, it adds A3 to A2, and the result is negative 98. Here, E represents the error in the result. As we can see, the value of A2 is rounded off. So this is a case of precision loss. In the second addition, it adds negative 98 to A1, and the result is 0. So this is a cancellation. So after the third addition, it computes the sum of the elements as 1.1 times 10 to negative 15, and the error is negative 1.2 times 10 to negative 15. So this is a very high relative error. Our insight is that to identify error-inducing inputs, we should explore the operations where precision loss and cancellation occur. We designed and implemented a tool named FPGen. This is an error-inducing input generator that uses symbolic execution. Specifically, it has 3 modules. Each module is represented by a color. The first module, in accuracy check injector, takes the program P as input, and it injects in accuracy checks to detect precision loss and cancellation. The second module, concretization and symbolic execution, iteratively partition the input variables into 2 groups. Input variables in one group are concretized with random values, and input variables in the other group are symbolized for symbolic execution. We then monitor the status of the symbolic execution engine. if it times out, then we're going to reduce the number of symbolic variables. And if terminates, then we redistribute concrete and symbolic variables and redo concretization and symbolic execution. So this process can be repeated as many times if until the time is out. The third module, error measurement, takes the input that generated by the symbolic execution, and it measures error triggered by each input to identify error-inducing inputs. In our evaluation, we collect a set of numerical programs that take multi-dimensional data as input. First, we include 3 summation programs that take arrays as input, and we include 9 matrix computation programs in Marshall library that take vectors and matrices as input. And lastly, we include 9 statistical functions from the JSL library that take arrays as input. We compare FPGA to 3 baselines. The first is the random generator. Second is the state-of-art generator S3FP. It is an error-inducing input generator that based on randomness. The third is a symbolic execution engine for floating point, CleFloat. This is also the symbolic execution engine we used in FPGA. This is the visualization of our experimental results. As we can see, the x-axis are the benchmarks, and the y-axis is the maximum error triggered by an input generator in a benchmark. The y-axis is in log scale. As you can see, in most of the program, FPGA triggered the highest error across 4 input generators. A summary on the results. Out of 21 programs, random and S3FP, they can trigger an error in 13 programs, and CleFloat cannot trigger an error in any of the programs, and FPGA trigger an error in 20 programs. Regarding to the magnitude of the error triggered by each input generator, FPGA triggers an input error that is around 10 to negative 6 on average in 20 programs. So it is 2 orders of magnitude larger than the state-of-the-art S3FP. To conclude, in our error-inducing input generation, we formulated precision loss and cancellation to enable symbolic execution for error-inducing floating point input generation. Second, we designed iterative concretization that manages the number of symbolic variables to scale symbolic execution. There's 2 directions for future work. Thank you.
We have time for a few questions.
Okay.
Anyone? So I was impressed. If you can go back a few slides and to show, the performance of the baselines, right? Random against FPGA, right? And I was impressed with the number of errors that the random was able to capture, right? And well, just wondering if you let random to run for as much as the other techniques, right? Or you just gave the same number of inputs to each one of them, right? So of course, in that case, random would finish much faster, I would guess, right? I would like you to just explain this setup where you executed random, especially because it performed so well apparently, right? Relatively, for example, CleFloat.
So basically for random basically we random sampling a few inputs in the input domain. Here with a time limit of 2 hours. So we iteratively sampling inputs in the input domain and compute the maximum error the random technique triggered in the benchmark.
So these 2 hours is also given to the other
Yes.
technique. I mean, it's the same time that
Yes.
you give to everyone, right?
Yes.
All
Yes,
right.
correct.
Okay, great. So that's pretty much, I mean, what the message you're saying, that there are some inputs, some errors here which are less likely to catch, right? Because random is not able, but symbolic execution is able to capture, right? Is that it?
Yes.
All right. I mean, anyone else? I mean, has questions? I mean, to Rui. Okay. If not, I mean, let's thank the speaker, right? And let's move on. I mean, to the next talk. Thank you very much, Rui.
Thank you.
So the next talk. The next talk will be given by Wing Lang. I study on the life cycle of Flaky tests, which is a huge problem in industry. Wing Lang is gonna talk more about that. I mean, joint work with Microsoft. So it's all yours, Wing.
Thanks for the introduction. Hello, everyone. So today I'll be talking about our work on a study on the life cycle of Flaky tests. My name is Wing. This work was done in collaboration with some folks from Microsoft, specifically Kavanch, Hitesh, and Suresh. So what is a Flaky test? A Flaky test is essentially a test that passes and fails when you run it in the same test scenario. On the right-hand side of the slide here, we actually have a Flaky test from a Microsoft product. This test actually, by itself, contains over 100 lines of code in this test class just by itself. And when the problem with this test is that at line 20, we would find that it can actually pass and fail. And so immediately, it's not exactly clear why this might be the case. So in order to understand this, let's kind of walk through the test a bit together. You can see actually that at lines 3 to 4, we're actually setting up a database. Around lines 6 to 8, we're actually adding some content to the database. And at line 10, we shut down the database. And then at line 13, we actually have this thread.sleep here. So essentially, we're waiting for something, but it's a little unclear immediately what this might be. And we'll revisit this once we actually go over the rest of the tests. At lines 14 to 15, we see that we're actually ensuring some file reader is actually killed before we start using it. And then at lines 17 to 20, we use the file reader and check whether or not some expected content was logged into some file. Still, again, at this point of the code, it's unclear why the expected content is missing sometimes. And it turns out, actually, it's very much related to line 13. In fact, what line 13 was meant for is actually to wait for some added content to be logged into the trace file. So as database executes, it actually will log some content into a trace file asynchronously. And then lines 17 to 20 checks whether or not some content was logged. In fact, when we actually see what the developers fix to kind of reduce the flakiness of this test, they actually suggest increasing the sleep time. Specifically, we see the developers change line 13 from 300 to 600. And the developer themselves even made a comment saying that they are fixing this flakiness by increasing the wait time before they check for the content. So some previous researchers who worked on Flaky tests would actually categorize this as an async wait Flaky test. Essentially, a test that makes an asynchronous call, but does not properly wait for the call to return before they start utilizing its resources. In general, though, Flaky tests of all kinds, including these async wait ones, are problematic for various reasons. And that includes wasting the developer's time in the sense that if a developer makes some recent change and a flaky test fails, they may think actually that it's because of their recent change. And because of that, they may spend time manually debugging a non-existent fault in their recent changes. And also just wasting machine resources to rerun the tests. So the goal of our work is actually to help these proprietary software developers with flaky tests. And we accomplish this by first performing a study that helps characterize flaky tests in these proprietary software. We then proceed to introduce an approach to help balance the runtime and frequency of flaky test failures caused specifically by asynchronous calls. In terms of our study, we actually look at 5 main categories of questions. The first one is on the idea of prevalence. So how prevalent flaky tests are and how they really impact the developer's workflow. The second one is on detectability. How many runs, I guess, are typically needed in order to detect flaky tests? The third one is on characteristics. So does test flakiness actually ever reoccur after developers fix them? How does the runtime of flaky tests sort of differ on passing and failing runs? And the fourth category that we looked at is actually on the categories of flaky test fixes themselves, specifically the root cause and location of these flaky test fixes. And finally, we take a look at the resolution of flaky tests. So how much time do developers take to actually fix these flaky tests, and how developers are fixing a specific type of these flaky tests. For the purpose of my presentation today, I'll focus largely just on the categories and resolution question. Specifically for categories, we see that the majority of the fixes for flaky tests are actually in the test code. We also see that the most common category of flaky test fixes is this async wait related category, where again, a flaky test makes an asynchronous call and doesn't properly wait for the call to return. And our findings here actually confirms what a previous study on flaky tests has found, specifically that test code is where the majority of the fixes are typically made, and async wait is the most common category. In terms of how developers are currently fixing flaky tests, specifically the async wait ones, we have actually seen that some people have proposed 3 different ways to actually address these issues. The first one is to create these synchronous interfaces. And the second one is to implement callback. And the third one is to implement polling. So at Microsoft, we actually see a number of developers implement callbacks and polling. Besides what was proposed, we actually observed 3 other ways that developers at Microsoft have been fixing these async wait related flaky tests. Specifically, we see developers increase the wait and timeout, sort of like the example I gave earlier. Another way is that the developers will remove some code that's related to the async wait call, either directly removing that call or just removing the test itself. And the third one is actually to mock these asynchronous calls. The one thing I would draw your attention to here, though, is that the most popular way that developers seem to prefer fixing these tests is actually just to increase the wait and timeout. Because of this, so now we have seen that the majority of these flaky tests are actually of the async wait category, and the majority of how developers prefer to fix them is to increase the wait and timeout. The goal of our approach is actually to automatically suggest some time values that developers should wait for these asynchronous calls, while at the same time minimizing the rate of flaky test failure and the test runtime. The way our approach works is done in 2 main steps. The first one is to obtain the flaky test failure rate for the time value set by the developer to sort of establish a baseline for what the flaky test failure rate currently is and what the test's runtime currently is. We then generate new time values based on the previous time values, flaky test failure rate, and the runtime of the test then. Specifically for our approach, we actually take as an input a flaky test along with its dependencies. So whatever we need in order to actually run the flaky test. We take the number of runs to measure the frequency of flaky test failures and the number of time values to try. And so in this example here, what we would do is we would actually run the test 100 times using the time value specified by the developer to obtain the flaky test failure rate and the runtime. We would then use that to generate a new time value based on the previous time values, flaky test failure rate, and runtime. So for an example, if the previous time value was set to be 300 milliseconds, and we find that the flaky test failure rate is 0, then the next time value we would try would be 150 milliseconds, essentially binary searching our way to the next time value. In the end, we will, for each of the time values we would try, we would output that time value along with the runtime of the test and the flaky test failure rate. When we actually apply our approach to 5 different async wait fixes of developers, we actually see that our approach can help reduce the running time of these tests on average by 38%. And we also see that for one of the tests, we can actually reduce it by up to 78%. And for 4 out of 5 of these tests, we actually see that once we change these time values, the flaky test failure rate isn't affected much, actually, in the sense that we can keep decreasing the time it takes to run the test, but the flaky test failure rate is actually not affected. So, and especially once we study the manual investigation, we actually, especially once we perform manual investigation on the fix, we actually see that developers really thought that changing the time value would have fixed the flaky tests or reduced at least the flaky test failure rate. In conclusion, we see that detecting flakiness is still very challenging. What developers claim as fixes are still often unreliable, and that async wait is one of the most common category of flaky tests in both open source and proprietary software. To help developers with this, we actually help by performing a study characterizing flaky tests and an approach to help them balance the runtime and frequency of their flaky test failures. Thanks. I'll take any questions at this point.
Thanks a lot, Wang. Very interesting talk, and I'm opening out, for questions. Anyone, questions?
Hello, this is Na. I'm looking at the questions on the Slido. It seems that we have several questions posted. And one of the questions is like, is optimizing the waiting time, not just the dressing up the peak? Shouldn't this code be replaced for a proper fix?
Yes, I think so what exactly I guess developers are doing here and claiming as fixes is largely sort of, it's not exactly completely going to remove the flakiness. I think that is very much true. The one thing I would say in terms of not doing fixes this way is that developers are going to be much less likely to be willing to just kind of accept any suggestions that you give them. Because in that case, you can see that I did mention some other ways of sort of fixing these kinds of flaky tests. And most of them are going to require quite a bit more changes. And these changes may not be something that developers will easily be acceptable to. As kind of we have seen from how developers at Microsoft were actually fixing these flaky tests at the moment.
Okay. Other questions? We still have time. So Wing, a quick question. It's about, actually the measurement, right? I had the impression that this pretty much, depends on what machine you run. You run this, right? If you have this new measurement, then you want to run your test, on a very fast machine or very slow machine. I don't know. You can change from one machine to the other, right? In the cloud. How?
It seems like you got muted at the end, Marcelo. But I think I understand. Or sorry, go ahead, Marcelo.
Yeah. No. My question is about the reliability of these measurements that you are making, right?
Yes.
If you change the machine where you're gonna run, right? That number that you computed may not be valid anymore, right? That's just a guess, right? Maybe you're wasting time, or maybe you're gonna create even more flakiness. You see?
Yes,
depending on the machine, if it's faster or slower.
That's a very good question, Marcelo. Essentially, there's 2 things I want to say on this. The first thing is that in terms of the evaluation, that was actually done on the continuous integration machines, essentially, where the developers themselves would actually be running their tests in order to determine if they can kind of merge their latest changes. The second thing is that the way we actually envision how developers will actually be using this is also to use it along with a benchmark. So if they actually run this, if for an example, we generate these values on a continuous integration machine, we would also run a small benchmark to see how those machines would perform on that benchmark. And whenever you switch to different machines, or if you use your own local machine, for an example, to run these tests, we would again run that small benchmark and actually fine tune the values that we've given before and adjust them accordingly based on how you perform on the benchmark.
Okay, thank you very much, Winga. That was a great talk, and let's move on into the next one, right? And the next speaker will be Andrei Miransky. So is your quantum program bug-free, right? And we're gonna talk about quantum programming, and I'm very excited.
Hi, Marcelo. This is Lei here. Can you hear me?
Okay, it's all yours, Andrei. All yours.
Thank you, Marcelo. Hello, everyone. My name is Lei. Today, I'd like to introduce you this exciting research work on behalf of my two other co-authors. We are all from Ryerson University, Canada. As you may know, that quantum computers are becoming more mainstream today, and more programmers started writing quantum programs. So one natural question arises: how should a quantum program be debugged? And that is what I will focus on today. First of all, let's see what happens when you run into a bug in a classical program. So we have a very simple example, a Python script on the left, and it has a typo. So if you run this script, it raises an exception and it prints out the stack trace. In the stack trace, you can see what type of the error and what variable you referenced, and also where it is. So the stack trace can help you or help a programmer to trace back the root cause of a bug. But things are quite different or difficult for quantum programmers. Why is that? Suppose you are writing a quantum program, say, for example, on the screen in Qiskit. You may ask yourself a question: how do you want to debug the quantum part of the program? And furthermore, are those existing debugging tactics for classical programs still applicable? Spoiler alert, it's a little bit tricky and challenging to debug a quantum program. To answer those questions, first, let's compare the fundamental differences between a CC and a QC. And allow me to quickly refresh your memory of what is the state of a CC. Basically, it's just a sequence of zeros and ones. If you have n bits, you can use n bits to represent one of 2 to the power of n states at a single time. But for QCs, a QC contains qubits. Qubit can be represented in bracket notation and can be captured as a superposition of orthonormal basis states 0 and 1. Here, the coefficient alpha and beta are called amplitude. Now, if you have n qubits, the n qubits can be 2 to the power of n different states in superposition. Now we see the reason why a qubit can be different. Because in superposition, a qubit can be in 2 different states at the same time until a merriment will cause it to collapse into one state or the other. The question is, which one will it collapse into? It's random, depending on the probability amplitude. Here, as an example, in the famous thought experiment, Schrödinger's cat, what is the chance that the cat can survive? 50%. Remember, those properties will make debugging a quantum program more challenging. In such a case, we need to check if a variable is in superposition or not. And there are 2 different scenarios. When the input state is unknown, for example, when it is generated as an output from another quantum program, then we do not have any general solutions. We have to make decisions on a case-by-case basis. But when the input state is known, for example, we have a circuit example on the right. It has 3 qubit register. The initial state is 0, 1, 0. Then the quantum state can be regenerated using quantum state tomography. due to the time limit, today we only seen one concrete example of superposition. But in the paper, we discussed the different debugging tactics based on the nature of quantum mechanics. For example, entanglement and no cloning. So if you want to read more details, please refer to the proceedings of our preprint online. All right, I think that concludes my talk today. Please email me if you want to discuss anything with us. Thank you for your attention and enjoy the rest of the evening.
We still have time for one or two questions, actually. Yeah, one question from anyone. Only I'm curious. I mean, to know. I mean, how you. I mean, how you measure how you run. I mean, these experiments, or you simulate these things, or I mean, the work is entirely. I mean, theoretical, right? I mean, do you run these in simulation or in quantum computers that you have some ability to rent time? I mean, what you actually do? And what kind of programs actually do you use? I mean, to experiment with? I mean, are there like test benchmarks?
That's a good question, Marcelo. For the first one, we have you can run quantum programs on two different platforms. One is the real quantum computer. The other one is simulator. So simulator can be used to debug your real quantum programs on quantum computers. But the limit is that because compared to quantum computers, classical computers can be slow. So say, for example, you run Shor's algorithm, you may only try some small numbers, but for large input states, it's not quite applicable or feasible on classical computers. I don't know, does that answer your question? I think you are muted.
All right. Okay, so the next speaker is going to be Bruno Lima. So if you can take this then. Bruno is gonna. Wow.
The next one is a demo video, so I can play the video myself.
So should I play this or
I can play it.
You can.
I can play it.
Okay, go ahead then, Martin, please.
Hi, my name is Bruno Lima. I'm here to give you a quick overview about DCO Analyzer. DCO Analyzer is a controllability and observability analysis tool for distributed system testing that checks if a system is locally observable and controllable. If not, can provide you the minimal number of coordination messages needed to achieve these properties. So, what is a distributed system? It is a system made up of many distributed components. These components can communicate between one another and with the environment through messengers. How to test this type of systems? Typically, you place a local tester at each component. Then, a central tester sets up these local testers with given scenarios, so they may find any potential errors with the components. In order to make this process time and resource efficient, the local testers need to run as independently as possible, so they don't need to constantly communicate with the central tester or the other local testers. To do this, they must keep their communication or coordination message as low as possible during the whole test process. So, what does it mean for a system to be locally observable and controllable, and how this contributes to minimize the extension messages? Be locally observable and controllable ensure that local testers can read and operate an assignment test independently. So local observability means that local testers can detect any conformance errors by themselves. Local controllability means that local testers can choose their own test inputs independently. These are crucial properties to keep coordination measures low and allow the tests to run as quick and efficient as possible. How to use DCO Analyzer? If you are a test engineer looking to test some scenarios or a system design that needs some help, first you open your favorite WML sequence diagram editor and draw your test scenario. Second, you open TCO Analyzer and upload your diagram. If it complies with WML metamodel, you'll be able to analyze the following properties: valid traces, unintended traces, local checkable traces, local controllability, local observability, and then determine coordination messages. Why is TCO Analyzer important? It is the first tool to be able to automatically analyze local controllability and observability and suggest the minimal number of coordination measures to correct problems. Do you want to know more or try it? Just follow the link on the screen and we'll find our tool to download and also some samples that you can use to try our tool. Thank you for your attention.
Okay, so let's move on quickly to Valentin, right? Valentin, are you on board? You're right there, right? So please take this stand and yeah. So welcome, Valentin. I'm gonna present a technical paper.
Okay. Hi, hello. Can you see my screen? Can you hear me well? Hello, I'm Valentin. I'm going to present you Enku, a gray box fuzzer. This is a joint work with Soo-Min Kim and Songkit Cha, my advisor. Gray box fuzzing has been very successful both in academia and in industry. For example, Google set up OSS Fuzz, which is continuously fuzzing many open source projects. But you could ask, why are we continuing doing research on gray box fuzzing? What is there left to improve? To answer this question, let's see how gray box fuzzing is working. Gray box fuzzer has seed-based fuzzers, meaning they have some test cases in a seed pool, which they modify to generate new test cases, which is then run by a program which has some outputs. The specificity of gray box fuzzer is that this output is not ignored. This output is used to decide whether or not the test case should be added to the seed pool or not. The fitness function is a function doing the decision of adding the test case to the seed pool or not. And we think the fitness function can be improved. Let's see what kind of feedback the fitness function could use. There are different kinds of feedback which have different costs, the cost being the time overhead over the program executions, and the no feedback function on the left side of this graph where the no feedback fuzzers like ZZF and BFF, basically black box fuzzers. On the right side, we have taint analysis, which is very costly but brings a lot of information. And in the middle, we have what has been found to be a good trade-off between cost and the benefits it brings, branch coverage. And its recent improvement, branch sheet count used by AFL and LibFuzzer. We think there is a space to improve branch coverage by having a feedback which can lead to better seed selection and thus better test case generation. Let's see how coverage-based fuzzing is working and how we can improve on it. The idea of coverage-based fuzzing is very simple. It says if there is a new branch in the test case we just ran, a branch which we never saw before, we add it to the seed pool. Let's take a very simple example. In this program, there are 4 branches. The 3 first branches are activated by the 3 first bytes. The first byte activates the first branch, the second byte the second branch, and the third byte the third branch. The fourth branch is activated when the 3 first branches are activated at the same time. Let's say we are starting to fuzz with test case A and B in our seed pool. Test case A and B triggers branch 1 and 2 respectively. Let's say we generate test case C, which triggers both branch 1 and 2. Let's say, test case C is not added to the seed pool by branch coverage because it doesn't have any new branch. Now let's say we generate test case D, which triggers the 3 branches at the same time. And in particular, it triggers a sub-branch, which is new, so it is added to the seed pool. However, test case D is quite unlikely to be generated because with test case A and B in the seed pool. It would be much more likely to generate test case D if we had test case C in the seed pool. However, as we say, test case C is ignored because it just combines already existing branches. It doesn't, so it is ignored by coverage-based fuzzing. Therefore, we would like a more informative fitness function in the sense that it takes into account combinations of branches. That's the goal of Enku, to build a fitness function which is more informative by taking in account combinations of branches. To do that, we first need to quantify difference between program execution, then making sure this quantification is both fast and adaptive. Adaptive in the sense that if I give you a quantity of 1, what does it mean in the particular context of this program? Let's start by seeing how we can quantify difference between program executions. First, we need to have a different representations of execution. As we saw for coverage-based fuzzing, each branch is considered independently from the other. Branch 1, new or not, branch 2, new or not. Here, for Enku, we take a point representation, meaning that each point represents how many times all branches were executed. For example, the 2 points mean both branches were executed twice. The 1 0 points means the first branch was executed once and the second branch was not executed. And once we have a point representation, we can quantify the difference between execution by using a distance. Here we use a Euclidean distance, which is a classical distance we use. Once we have a distance representation, it can directly include or detect the combinatorial difference. For example, if in our seed pool we have the 1 0 and 0 1 points, it already covers both branches. So the 2 points and the 5 1 points will not be detected as new by coverage-based fuzzers like AFL and LeafFuzzer. But using a distance approach, we can directly see that the 2 point is very different than the 1 0 and 0 1 points. So here already we achieved our goal of detecting combinatorial difference. However, this is not enough for gray box fuzzers because gray box fuzzers care about seeing the difference between a seed pool and the new test case which we generate. So we need a point to pool distance. For Enku, we set the point to pool distance as a minimum point to point distance, meaning that for each new test case we generate, we need to compute the distance to all the seeds in the seed pool. The first seed, the second seed, and the third seed. Here, the third seed is the minimum, so it is our point to pool. The idea is a minimum point to point distance is going to be what's going to be brought by this new test case if it is added to the seed pool. Here we already we have a distance base to base our fitness function on. But before building more our fitness function, we need to make sure our fitness function is fast enough. Why? Because the fitness function is computed for every test case. Thus, if the fitness function is too slow, the whole is going to have a huge negative impact on the fuzzer. And sadly, the Euclidean distance is not practical. Why? Because the Euclidean distance cost is linear with the number of branches in our program. The more branches we have, the more costly the Euclidean distance is. And usually there are thousands or even tens of thousands of branches in the program we fuzz. Thus, we need to reduce the number of branches in our program. We can do that using a technique called dimensional reduction, which finds representative branches, usually 10 or 20 representative branches. And then we have a practical distance, which is practical to use for gray box fuzzing. You can see details on the dimensional reduction technique we use in our paper, which we call. So now we have a practical Euclidean distance. We can go on building our fitness function. To remind you, the coverage-based fitness function is if there is a new branch, then we add the test case to the seed pool. For Enku, we have this distance to base our decision on. We say if the point to pool distance is above a threshold, then we add the test case to the seed pool. We set the threshold as the minimum inter-seed distance, meaning that we compute the distance between all pairs of seeds. And we set the threshold as the minimum distance. Why? The intuition the minimum distance is what we have is the minimum we're accepting in the past, so it will be the minimum we accept in the future. So now we have a fitness function which works. Let's evaluate it. We evaluate Enku based on the benchmark from Coil AFL, a paper published in 2018. We run each experiment 6 times for 24 hours, which makes a total of more than 7 years of experiments. The first question we ask is this new fitness function effective? To answer this question, we run Enku with a classical coverage-based fitness function and with a new distance-based fitness function, which we just developed. On the left is where the new distance-based fitness function is worse, and in the right is where it is better. We see that when it's worse, it's only slightly worse, but when it's better, it can be much better, as much as 4 times more crash is found. which makes on average Anku find the distance-based fitness function finding more than.
You need to wrap up, Valentin.
Sorry?
You need to wrap up. You need to wrap up.
Okay. So we also compared Anku to AFL, and the insight is usually Anku and AFL have reach the same coverage, but Anku find 41% more crashes, which confirms our intuition that not only coverage matters, but also combination of branches matter. And what is even more impressive is that AFL generates 35% more crashes than Anku. So in conclusion, we show that there is a problem with coverage-based fuzzer because they don't take in account combinations. And we design Anku, which takes in account combination while being fast and adaptive. And when we evaluate Anku compared to AFL, we show that although it has generated, Anku find 41% more crashes. Thank you for listening to my talk, and I will take questions.
I'm sure that there are a bunch of interesting questions, but I mean, we don't have much time to do right now, right? I mean, I just wonder. I mean, if you are running in process fuzzing like lib fuzzer, or it's like out of process fuzzing like AFL, like
we use the same technique as AFL.
Comparison, right?
Yes, we use the same technique as AFL, out of process.
Out of process, right? All right.
But
so
as a side note, LibFuzzer also accepts out of process now.
All right. So let's take the rest of questions offline, Valentin. I'm sorry. I mean, we run out of time. Right. Let's call Richard demo right now. So Richard. So Martin, can you start playing Richard demo?
Greetings. I'm Richard Rutledge, and I'm here to preview a live demonstration of our PG-CLE toolset. PG-CLE is an implementation of progressive symbolic execution, a general framework for the exploration of program behavior through dynamic adaptation of unconstrained program state with a selectable balance between coverage and feasibility. In our demonstration, we will apply PG-CLE to several experiments from our ICSE 19 paper. Suppose we have a dynamic analysis requiring inputs to drive every possible program behavior subject to a coverage criteria. By design, symbolic execution is particularly adept at finding inputs satisfying such criteria due to its systematic exploration of all program paths. But in practice, coverage is often limited due to path explosion or solver limitations. One way to get more coverage is to unconstrain more state. Suppose we have a program P with an interprocedural control flow graph as depicted here. We have three functions, main, foo, and complex. Each box represents a basic block, and each arrow represents branches between blocks. Main calls foo with a set of input parameters. In turn, foo calls complex from a loop header. In our example, the lidded body of complex contains code subject to a classic symbolic execution limitation. To obtain maximum coverage, PG-CLE will progressively add unconstrained state and execute increasingly smaller pieces of P, while only persisting test cases that improve the coverage metric. It starts with standard dynamic symbolic execution at main with symbolic inputs. Then, from each function of P reaching a program point with missing coverage, PG-CLE executes the function with unconstrained global state and symbolic function parameters. The third phase substitutes unconstraining stubs at a function's call sites. These stubs return a symbolic value and unconstrained output parameters and global state. Finally, for each function containing missing coverage, PG-CLE unconstrains local state and begins execution at each reaching basic block. The progressive addition of unconstrained state allows PG-CLE to generate test cases maximizing coverage. Obviously, there's a trade-off between coverage and feasibility of the generated tests because of the behavior of over-approximation. A test case is infeasible if no program input executed from program main reaches the test case entry point with the test case program state. Depending on the effects of coverage versus feasibility on the targeted dynamic analysis, one can tune this trade-off accordingly. If you want to hear more and ask questions, make sure to attend the demo session, or check out our tool, which you can find as a Docker image and a permanent archive at the sites listed here.
Hi, everyone.
Go ahead, Valentin, or Carl right now, right?
Yep, thank you so much. Yep, thank you so much. Alrighty, you should be able to see my screen. Thank you for introducing me, Marcelo. Hi, my name is Carl, and today I'll be giving a presentation on our paper Blending Kinematic and Software Models for Tighter Reachability Analysis. As autonomous mobile robots have increased in popularity, so has it become more critical to accurately predict what states they enter during their operation. A reachable set is a common tool used to provide such predictions. Computing a reachable set starts with the robot state Q at time ti. A typical robot state consists of position and velocity. You then apply the set of inputs U, where an input consists of actions like acceleration and steering angle, to compute all possible future states of the robot. The area or volume these future states cover represents the reachable set. You then simply repeat this process as many times as you need until you reach the time horizon you desire. Traditionally, the set of inputs U has been instantiated with the system's physical attributes. For example, consider steering angle. The input would be instantiated as all steering angles between the physical minimum and maximum steering angle. The problem is that as we move towards autonomy, many systems rely more and more on sophisticated software. A great example of this is a modern car, which has close to 100 million lines of code. This work's insight is that the precision of a reachable set could be dramatically higher by considering the constraints imposed by software. By only considering the physical attributes of a system, you're likely to overestimate its capabilities and thus over-approximate its reachable set. Over-approximating reachable sets have two serious consequences. First, they may result in the vehicle being overly cautious by avoiding obstacles they could not possibly hit, resulting in inefficient behavior. And second, they might be overly aggressive, resulting in unsafe behavior, for example, estimating that it can pass another vehicle where it actually cannot. So how do we propose on generating these more accurate reachable sets? Well, previously one would use the robot type and physical bounds to compute the reachable set. This information is still important, but it's only part of the puzzle. The second part is to look at the software or program controlling the robot. Our approach takes, among other details, the program and the program variables which control the robot's physical behavior. Using the program, we compute the call graph and identify the nodes in the call graph that contain the program variables which control the physical behavior of the robot. We then apply interval analysis to these nodes. Interval analysis computes a lower and upper bound for a given program variable. These bounds are propagated up through the call graph, which results in conservative software bounds for each of the given program variables. Using these new constraints, we compute the reachable set. The preliminary results show that there's a dramatic reduction between what the robot is physically capable of doing and what the software is capable of commanding the robot to do. For example, when you consider the differential drive robot in the first row, we notice that the maximum physical velocity is -1 meters per second. However, the software is not capable of publishing a negative velocity. Similarly, reductions were found in the quadrotor that we studied. Using these new bounds, we computed the reachable set. We found that for the differential drive robot that we studied, there was a 91% reduction in the reachable set when considering the software bounds. Similarly, we found a 77% reduction in the total volume of the new reachable set for the quadrotor. We can visualize these reductions. For example, we showed that the reachable set for the differential drive robot on the right, we showed that the reachable set using the physical bounds is a dotted line and the reachable set using the software bounds as a solid line. We find that for each time step, we can see a clear reduction in the reachable set. Moreover, we see that the reachable set at t equals 3 for the software bounds is smaller than the reachable set for t equals 2 using the physical bounds. Additionally, when we consider the quadrotor, we again see reductions in the reachable set. Here we show the quadrotor as a dark blue dot in the middle, the light red shade is the reachable set with the physical bounds, and the blue darker shade is the reachable set when considering the software bounds. Thank you for listening to my talk, where our key takeaway is that the precision of a reachable set used by autonomous vehicles could be dramatically higher when considering the constraints imposed by software. We propose an approach for uncovering and applying these constraints. Thank you, and I will take any questions.
Any questions? We have time for one question. Anybody? So, Carl, what exactly the goal is reachability is finding line conflicts of objects in the trajectory of these dots. I mean, is this the main goal? I mean, find what if they're gonna hit something, and yeah.
Sure, I think there was a little bit of some audio problems there, but I think a little bit of some audio to the question. So why do we need these reachable sets, and what are they used for? Right now, what they're actually used for is a variety of things in autonomous systems. One of the big ones is collision avoidance, because what a reachable set does is it basically tells you all the possible locations you could be in any future state. And if all your possible locations, for instance, are colliding with an obstacle, you know that that's a very bad state that you're in. And so you're trying to maximize the amount of this reachable set that's not going to be colliding at any given time. And so by over approximating that, you basically have a less reliable source of information. And the goal of this work is to bring the software constraints that are imposed on these systems into the computation so that we get a much more accurate reachable set when we're doing the computation.
Sure. So out of curiosity, I mean, how this is tested? I mean, is this with simulation? And people also discretize the input domains like physical bounds that you mentioned. It looked to me that one simple thing to do was to discretize inputs. I mean, to instead of using like floating points, using the or something. Easier to analyze.
Yeah, I'm sorry. I actually struggled to hear that. I'm not sure if it's on my side, but I did hear something there about the simulation, and these results were computed in simulation. Yes, I'm sorry if that didn't answer the question. I was struggling to hear the audio.
Marcelo, your audio is very bad. I think it's for everybody, and we have some echo in every answer. Just to warn you.
I will just on that note, I will be looking at the different channels available for ICSI afterwards to answer anyone's questions. So I will be around to answer the questions.
All right. With that, we finished this, right? And I guess this one is gonna be like a student, and we can move there and try to enjoy ourselves, and I hope we can see each other.
Marcelo, we almost